before we break for lunch. Yeah. You have to raise your voice a little bit. Yeah, value iteration, okay. It's the same method. Reinforcement learning is the framework. The value iteration and the policy iteration is how you solve those equations like the Bellman error equation and the control policy. So when you say value iteration or policy iteration, you are trying to solve those equations using iterative approach. That's all it is. It's still oral method, reinforcement method. That's what these guys do, machine learning people do. The CS people, computer science. You see? And that's an offline method. Whereas we have to use it for control, then you have to use what I was doing. We call that as time driven. Remember I gave you the code. Intro to oral, there are two codes. One is the value or policy iteration, the other code is for the time driven. Without using policy or value iteration. I don't know how many of you run that code. The one that Dr. Bera gave, the intro to oral, there are two codes for two examples, right? Two plans, yeah. So did anybody look at the code? I think I encourage you to look at it. I think everybody got that code, right? Yeah, I think I would rather run. So why don't you spend this time, before you come to the afternoon class, why don't you run it? So that has the value of policy iteration. The name iteration means you are solving those equations. The HJB equation or whatever by iteration. Okay? Any other questions, guys, before we break? All right, we are done. Nobody is raising their voice, so we stop it here. So we are early today by 15 minutes. To compensate those days we went past the 12 o'clock. So we will be here again. Did anybody run that intro to oral? There are two folders, at least. One for value iteration and stuff, policy iteration. The other one is basically the time driven. Actor critique time driven. With genome. Yeah, discrete time. Because that's what we are trying to use there. So I want you to run it, feel it works, but I'm just saying that you see how it is being written and how the critique is being updated. I think it's very critical because all that concepts we are using in our slides, the only thing we do is we extended that to with an identifier. And so identifier relaxes the G also. Right, so it's important.
Good afternoon to all of you. So welcome to the assignment 2. We are going to solve or we are going to discuss basically. And this is the tutorial 2 we are going to conduct. But let me tell you that as I have suggested that before going to do this assignment 2, once again you look into the basic program of RL once again. Because that folder is already shared, so you just see that how the basic programming related to RL is working, okay? And now we will solve this assignment to be different way, what I thought. Till now you are following Sad's slides, okay? And today the problems related to the quantization basically we have. But have you looked any of the paper written by Sad? Then you will find that in paper in more details in simulation section you will find that the parameters are given. Okay, it is discussed in a more elaborately. So that's why you will find that today what I did, I'll come to this problem little bit later, but just you see that one problem we have given in this way. You see the problem 3, you see what it is written, that consider the system given in 4 and 5. Basically here two systems are given, one discrete time LTI system which is a linear one, okay, and another is given continuous time dynamics of two linked robot R. So these two systems is given, and now you see what in the problem 3 it is written, that is consider the system given in 4 and 5. Design a finite horizon optimal controller which is discussed in this particular paper, that is neural network based finite horizon optimal control of uncertain affine nonlinear discrete time systems. Okay. So I think I have already shared you know that particular paper. One second, another paper I want to show you that is related to quantization basically. This paper, have you seen? This paper particularly? You will find that this also sir has discussed, this one, that neural network based finite horizon optimal control of uncertain affine nonlinear discrete time systems. Okay. And someone is asking, you were asking that particularly how the parameters for that delay and this is actually given in the paper only. You will find that the stability condition, some bounds are there, and that bounds are declared there to establish the stability or guarantee the stability of the system. Okay. Once again, I will come to that. So here you will find that whatever the sir has discussed, everything is given more systematically. You can go through it such that you can understand. Okay. So this paper already I have shared. You just look into it, you open it and you see. Then I will come to the quantization part. You see, as the sir said, there is a Bellman error, then the total error, everything you will find here very clearly, and it is written very nicely, so you can follow it. And the way sir told that how you will find out the stability, the steps, everything is given clearly here. And more is that if you go to the simulation section, you see this is the bounds what we are talking about, 42, 43, 44 equation number. So you will find that exactly these bounds are also defined there at the beginning. So these are the two examples. Here it is there. Another is the tooling manipulator, what sir told. So these are the parameters. You will find that it is more details it is there, that what is the simulation time, what Q, R, all these values are chosen, what is the initial condition, what is the initial admissible control, that also it is mentioned clearly. Okay. So this paper you look into, I am showing you another thing very quickly. You just go through it, then I will come to the original assignment. And have you went through little bit time, have you found to see the sir's book, what I have sent, book? That also you just open now. Then it will be easy for you to track what it is going and also to see the papers. That is very important to. So this is a chapter I am talking about, optimal control of unknown quantized network control system. This is the particular chapter I am talking about, 4, and the simulations we will do from this chapter only, chapter 4. Optimal control of unknown quantized network control system. This book you will find that the confirmation mail what I sent, with that the attachment is there. You just, if you have not downloaded, you download it and then you see. Little bit you go through it, then we will come to the problem. Just to see that what are the topics are already presented, you can correlate it with this particular chapter or not. So if you want to do this particular problem, if you want to handle this particular problem, you need to understand the quantizer also. So the equation related to quantizer you have to understand. So just you see this figure and see this equation, how you take some values, arbitrary values, and you match that whether you are able to correlate. Then you will find that dynamic quantizer is also represented, that also you see. And mainly you see the flow charts also, then flow chart will be helpful to understand that particular programming also. Okay. So this is the paper also you can see, okay, that this finite horizon near optimal output feedback. Here actually output feedback what sir told, that means observer, this part. This is a particular paper where sir told about the output feedback, and also here one important thing. Can you remember the fact sir told that one important thing, whether you can remember it or not, that that non-quadratic functional we have used. What is the, can you tell what is the motivation behind it to use this particular non-quadratic functional in the cost function? Yes. Okay, so now let us come to the particular problem what we are going to deal with, and just I will tell you that many of you may be having some little bit of confusion that which folder, which particular program, this confusion is there. Let me tell you. You see, for the quantization we will take the same system, that is the batch reactor system, and we are going to that particular programming where it is actually in your case you will find that assignment 2 codes are there. Okay, here only you have to open this chapter 4.1. This is the, sorry, this is the one you have to open, chapter 4.1. Okay, then you may be surprised to see that why these many other subroutines are there. If you see the main program, like now we have to use the actor critic, all these network. Actually inside program, this actor network, critic network, all these things are not. Even you will find that for the nonlinear case, the system is defined in a subroutine, okay, not in the main program. So whenever you will, like here you see action NN, then the activation vector. So all these are critic NN based argument, delay. Okay, so these are all H vector, H matrix. What the H matrix you have constructed, everything they have defined as a subroutine. So that's why when you will read the main program, you have to identify that what subroutine has been called, and your work is to see that subroutine, that what it is written inside. Then only you can correlate that whatever the actor network you have designed for that particular system, that is defined there. You have to see the steps, then only you can understand. That's why I told you to see the book as well as the presentation as well as this particular programming. If you keep it side by side, you will find that everything you can identify at least. First you identify that which module is written for what. If you are able to identify that, in the next step you can build your logic, or you will try to find the logic that how the programming has been written. First step, you identify all the required subroutines to run that particular program. Like I am coming to the programming 4.1, you see. So here these are the bounds actually which is defined as already I have shown in the. So you see here delay, they are doing the import data delay.mat. So you will find that one MATLAB file they have generated, and from there actually the delay and the packet loss, that particular thing are imported, and this is known to you. That you see it is written already, that continuous time batch reactor system. Then you see here one function has been defined, myFun. In already you will find that it is defined as a functions there, and you have to identify that what is the need of that. And as I told you that if you want to And similar thing has been proposed for nonlinear system also, but here for the programming what we have provided, that is 4.2, it is not for the tooling manipulator. Okay, it is for this particular system. The 4.2 programming. This is the system for which the nonlinear system, the quantization based control, adaptive control has been proposed, and that you can look into. And if time permits, after understanding this, then you can change this nonlinear system to the tooling manipulator. Tooling manipulator is not there in the folder. Only you will find that batch reactor and the nonlinear system here. This one, these are the two things are there. Not the manipulator program is there. So manipulator program, if time permits today, but later on you can try it. But at least these two programming you see. First now I am telling that those who have not run the RL programming, that you run first, that you do. Then you come to this one. First you see the output of the RL program and you analyze that whether you are able to understand the basic RL based programming or not. Okay, then we will come to this.
So in the RL program, they have written that some equation 23, equation 24 for the world for the integration. But we can't make that which paper it is referred or which.
Yeah, that is 2012.
Sir said about
To NCS. Yeah, remember there is the Travis. So we can type.
you just tell me.
Explorer time-driven. Travis.
TR.
Yeah, time-driven. Let's see. Ulsa.
No, actually one paper I shared na, in the group. No, not this one. Earlier one paper I shared. No? Oh, 1 second.
That is the time-driven optimal control by Travis, and that's also when transactions on the network. They were just showing them in intro.
Okay, we can download that.
So you have to download maybe time. I would say time-driven optimal control. And you said Travis and my name is T-R-A-V-I-S. Tricks. E-I-E-R-K-S. Space.
Acha. KS only and Jagannath. This one? Here?
Let's see what that one is. Yeah. Maybe more than citation wise. Let's see. Yeah, that's it. This is it.
So I am posting this one in the group. You just see.
That's it. 2004. So this paper is the classical paper without any NCS. Okay? So I think you may want to look at it. This is just for the time-based, like what I just said, instead of value iteration. So that has a separate folder I gave you. Here we assume G is known. Remember we talked about it. F is unknown. Yeah, G is known, and you will see this is basic how you get the optimality.
So this is for the continuous and iteration.
That's a different one. This is the second folder, discrete time.
Main one.
Yeah. So take a look at that paper. Yeah, if you share it. The value iteration paper, I can share. Maybe I can find that and email you. You know. So you have that paper. The other one, the value iteration paper. Yeah, maybe I can send you. Maybe you would download this and we can share this one. This is the RL part. Got it? That's the paper, right?
Yeah, that's why it is already mentioned. I'm searching for that. So, sir, why you have used the term that is time-based policy update?
It's like a traditional time-based means once a sampling instant you're updating.
Oh, then inside that you are updating. Okay.
Instead of doing that multiple times, right? Yeah. That's what the value of policy. So next slide shows it works for when you have a large number of iterations, but if you don't use it, it goes
It will diverge.
There are two examples, right? One is the linear, other one is a non-linear system. Right. No, it's just one together. But the dimensions is based on how many neurons you select. So the number of neurons will dictate the dimension of the network, right? Just for normally you need to have many iterations, but here is just one. And your own, like how many based on number of neurons you can change. Oh yeah. And you know what you can do is you can put some intermediate things, and you want to see the plot how the values are changed in the program MATLAB. You can try to do that. That's why I said a while ago, make sure that you copy the original code and then you rename the one, so that way in case if you mess it up, you always go back to the original. Right, that's what she was asking. It's just a test. Just test. Yeah. So maybe you want to run that main program. So there are two, one for two examples. You run it and see if it matches with your result, and then what you do is you go through the MATLAB code and see what each of those portions are doing. To understand. You see what I'm saying? Yeah. First run it without as it is. And then what you do is you put some commands in between and see what changes. Yeah. So have you run that one? Yeah, it's working, right? So run it. Let's see what it does. Let's not just so you know. So it is showing the states after working. So now what you can do, yeah. So what you can do is you can actually now go back and the code and see why is it 1 to 1. Like you can put some commands in between. The ones that you are aware of, you see at what values are its rules changed. You know? Right. It's a regulation that is right. So that becomes a track. So the tracking you have to define. Maybe why don't you hold that question? Let us first cover this. Then we'll talk about it. Basically, what you have to do is, I mentioned tracking is a little more easy problem because you have to have two terms. In the regulation, you're only using the feedback. That's u star equal to minus half r inverse, right? In tracking, there's an additional term will come. That term is a function of the trajectory. The one that's like what you were saying, the trajectory that you were saying. Yeah, that's it. That is right. So what happens is you have to find that term. Sometimes that term is a function of the dynamics. So the dynamics is not known. So what we normally do is you have to create another argumentative system. So the trajectory has to be created in a way, and then you take the argumentative system as the error dynamics between the state and the desired value, and then you put another one which is the trajectory as part of it. Okay? So function of time as part of that design. Yeah.
But if you keep the same these two arguments pursue the dimensions.
Right.
It is going forward the dimensions.
Right. But you see, it's not just the trajectory dynamics you are talking. It is how that is playing when you remember I said two terms, right? The term that goes before the term that brings in, even though it's tracking, it brings in the dynamics of the not just the trajectory dynamics, it's also a function of the, yeah, it means, so there are two terms for tracking. One term for regulation, which is what you are doing. The tracking, what you are doing is you're mapping the tracking problem into regulation. And that's where you create that augmented system. So maybe what I will do is one of those times, I will bring up some example and then I will show you how to rewrite this code. But none of the codes is given to you for tracking. We are not having tracking in this course. But what you can do is I'll give you a suggestion for a paper. Maybe I'll talk about it. Then you can, yeah, and then you convert it. It's not that hard. So you're mapping a tracking problem into a regulation problem by doing the documentation. That's all we need to do. That step, once you do it, everything will work. You see what I'm saying? And you vary, like you said, you can vary the state of charge, what is the desired profile, any way you want it. It doesn't have to be a constant value. You can say after some time I'm changing like this or so we are not covering because we have covered quite a bit on the regulation. Now let's do the regulation before we get into tracking because that's a little more difficult. Remember I said that. Yeah, because that's why you get an additional term in there. And you need to know how you derive that additional term. We haven't talked about it, unfortunately. Okay? And so we will do that at the end of it. So hang in there. What that portion of the code is doing that Sar was telling you. Remember, okay, this portion is doing this portion is doing that. So that's what you guys have to do, unfortunately, because even any book you take, you would not be able to, when you go through the code, because people write with different styles. Remember, that's what we were talking about. People write in different styles. So this style was mainly everything is mapped into subroutines, like, different. So they are being called into the main program. You see? And so this is the way it was written. So different people write it in different ways. Some people put everything in the same program. Some people write it because the benefit is, I'll tell you, is you can change the system. You don't have to change the main program. You change and then you can call this. So you can, see, that makes it easier. The other thing is the controller. Let's say you have a system. Now let's say I want to have a different controller. I want to, I want to run. It's easier because you have a system. You call the same system routine into a different code for the controller. So this is why everything is typically modularized. Okay. So there are two ways you learn. One is make sure you get the commands, put some commands inside, and you run it and learn or understand what that code is doing. You see? The main thing is you have to make sure it works. The versions match and all that. Once you get that, then you can do all these things and then you learn from it. Then, no, that's one thing. Second is, remember, unless you do that, you can't make changes like what we are discussing. Let's say if I want to do tracking, what changes do I make? You won't be able to understand. So this is what I suggest you to. Okay, so spend some time. Be patient with it because at least it's working. And don't overwrite the code because then it's a problem if you make a mistake. So make sure you save the original stuff somewhere and you copy it into some name and then you play with it. Because I have done many times some changes and something blows up and you don't know what changes you made. It's like learning rate, you're playing with those kind of things and suddenly it blows up and you won't know what causing this blow up, right? So keep that in mind, okay?
Okay,
Do it